Mark gave a very great lecture about this genomics. I learned a lot. I didn't know this genomics, genetics, this analysis has progressed so much. I've been trying to keep up with this. I did a little bit research on this at the beginning, actually, about 20 years. As a physicist, you can do anything, right? It's all statistical analysis. So we tried a little bit, I tried a little bit of genetic, but then I decided to do something else. But so I knew a little bit about how all these algorithms, all these things going on, but I didn't know it's an incredible, now more complex. But that's what one would expect from the development of science. Everything will become more complex the more you look at. It's never the end. As I remember, I told you, there's no ending in science. There's only has up and down. Sometimes it becomes very hot, fashionable. Sometimes it's a little bottleneck. People get a little bit frustrated. But then after a while, it will come back again. It's always like that. It's never ending. And it's always new discovery, new excitement. So I think you can sense this is a kind of reason why we have a science camp. Science research is so much fun. And you never worry about you don't have a good problem. You always have a good problem. It's a question of whether you're looking for it or not. And you always find one, and you always find an incredible puzzle to solve. And we already hear this puzzle is very interesting, very important, but very challenging. So I hope all you enjoy the talk very much, like I did. And so now we are changing a little bit direction. And the next speaker is Professor Xie Dabin 教授 from National Cheng-Kung University. Professor Xie, I know him for quite a number of years. I actually started when I was in charge of a national program for nanoscience and technology. That's 2004, 03, 04. We started a national program. I was actually the executive director for that program. So we call for research proposal, and we give out the grant. It's very competitive. At that time, this is the most, the project that give most money. And they are very competitive, and Professor Xie was already one of the project, the principal investigator, and then he has several. He was doing very well in this nanoscience. So some people ask me what this national program has done. I told them one of the most important things, we have actually incubated many young researchers at that time, young startup assistant professor. Now they all become chair professors. All of this, about maybe I can count at least 12, a dozen. They all doing very well in this nanoscience and in all their respective area. And Professor Xie is now our expert in nanomedicine. He has many great inventions in nanomedicine. And I'm glad and also worry for him to be the minister, the deputy minister of science and technology. When he took the job last year, I congratulate him, but ask him to take care of his health. It's a very tiring job. It's a lot of heavy load and many things on his shoulder. As he mentioned yesterday, he has to deal with the legislator. This is a very heavy job. But he is doing very well, and we are glad that we have a very capable scientist in that administration. And so now, of course, he wants to share with us his thoughts on precision health And of course, nano medicine is exactly for that precision health, targeted for precision health. And so I will not go through his bio, but I just mention the latest award. He has many awards, as you can see from his CV. The latest award is the Xu Youxiang Chair for Nanoscience and Technology. That's a very prestigious award. And so let's welcome Professor Xie.
Thank you. Thank you, Professor Li, for the introduction. So today I'm going to talk about the two topics. One is about the nanoscopic precision and how this could help the precision medicine and precision health. And the second part would be the macroscopic policy, how we accelerate the translation from the fundamental science to clinic and to applications. And so first part, I think I would like to talk more about the funny side about the nanoscopic precision. And before that, I will talk about some of the old story and new story, which may be dated 30 or 40 years ago. My failure story. And so this is the outline about today's talk, precision medicine, and how it converted to the industrial development, and Taiwan's advantage and challenge, and finally the expectation. But I think before these kind of policy issues, I will talk more about this. You know, not long ago, Taiwan just celebrated the discovery of the horizon event of the black hole, Heidong. And together with the celebration of the launch of a satellite system consisting of 6 Format 7 that can provide 3-dimensional structure of our planet Earth every day. However, if you look down into our body from the space exploration, we know how tiny we are in the universe. However, if you look inside our body, then we would say how big we are. So we are constituted of a lot of atoms, and within the assembly of these atoms become the biological molecules that do a lot of functional things in our body. So if you look at the movie, you would inspire by the beautiful cartoons of all these molecules. For example, this is the epidermal growth factor we just mentioned yesterday. And they just like molecular machines, and they dimerization, and then they send signal, growth signal to the underlying of the intracellular cascade, and then providing information for cell to grow and to divide. However, if you got a mutation, for example, this molecule become a tyrosine, and then the hydrophilicity become a hydrophobicity, and that will actually greatly change the folding and the dynamic of the molecule. And if you look macroscopically, you will see there's a proximity of between the between the two dimers, and then the signal would be constitutively activate regardless of the growth factor, and that's why your tumor cell continues to grow. Okay, all these things happen so precisely at the angstrom level. Do you know how big it is? 10 to the minus of 10 meter. So how can we tangle this kind of mutation? So people trying to envision what is a molecule really look like. So everybody all say, to see is to believe, right? So is this a cartoon, or this is a real structure? So about 6 years ago, 2013, I established a center in National Cheng Kung University. I call it IMANI, the International Institute of Macromolecule Analysis and Nanomedicine Innovations. So the idea is we provide a cryo-electron microscope, and then NCKU already have the 600 NMR and the X-ray, and then we collaborate with synchrotron radiation center to form a collaborative framework to resolve the macromolecules in atomic resolution. And what is that to do with precision medicine? So this is electron microscope. Under the electron microscope, it looked like a two-dimensional pictures of virus or proteins, etc. So how can you resolve these electron microscope image into a three-dimensional structure of a protein molecule? Anybody got an idea here? If you got, then you got a Nobel Prize, 2017. Okay. So there's a lot of different algorithms being developed. And the idea is actually quite simple and straightforward. So the idea is, instead of drawing the proteins onto a film that we normally do for electron microscope, these guys use water to host the protein. So you basically dissolve protein in water, and then by inside the grid, you put your samples, and then you quickly blot the grid. Then there will be a thin film of water between the grid that will host all the different kind of proteins within. And then you put this thing into the electron microscope. So then the electron beam will kind of bombardment from the electron gun and then become an image like this. So this is what you got normally in an electron microscope. But you will say, wow, this is kind of so blurred. Even worse than the ancient black and white TV, right? So how can you make a very clear picture? So people start to think, if I got an image that is so blurred, but because there's millions of proteins on that particular grid, many proteins of the same structure. So if I could find the same protein, and then I can stack the image together, and then the noise would kind of decline rapidly. Then you finally got a much higher resolution picture. So all these are computational work. And the protein part is biological people. So you should shake hands with your neighbor if he is an electric engineer. And the same for the electric engineer, to shake hands with your neighbor if he is a biologist or a medical doctor. So that's one thing. So you can enhance the resolution by stacking images. And there are even more into this. For example, when you look at a particular image, actually it's a stacking of a lot of images because of the time resolution. And so there was a mathematical algorithm to kind of weighting the fidelity of each image in between the different frames. So there's a lot of work, mathematicians that could actually participate. Then all the proteins actually, when they dissolve in water and then put into the electron microscope, they are oriented at different angles, maybe like this or like this or like this, right? So people use the pixel calculating algorithm to kind of classify whether they are standing up or they are lying down at different angles. And finally, after stacking, you got high resolution of different angles. Then you know how to do, right? You do the Fourier transformation, and in the Fourier space, you do the three-dimensional reconstitution. Then you got a three-dimensional image of a molecule. Then you find where the mutation is, and then you design the drug to change the protein folding. Then you become a rich man. So this is how kind of interdisciplinary collaboration between mathematics, between engineer, between physics, and between biologists and medical doctor, they can do great things. Okay, the other part about precision medicine is all the proteins, as I mentioned in the cryo-electron microscope, they actually originate from a DNA map, right? So the DNA transcribe, become a messenger RNA, then translate, become a protein. This is called central dogma. So how big, how diverse is our DNA? You know, all the DNA is constituted of the ATCG, right? 4 different kinds of base. So how big is the diversity? I think smart like you should be able to calculate, right? Or in the immediate, it's 4 to the 3 giga of the diversity. That's why you don't look alike as your neighbor, right? So because there's a lot of diversity. And for these genes to take function, some of the genes actually become protein. And how you translate a gene to a protein? You know, if you write codes, you know that what is called byte. A byte is 8 bit, right? Defined by ASCII code. But in biology, since you have ATCG, so the calculation is not binary, but rather quaternary. So you only need 3 bits to become a byte. That's why we have a lot of different diversity in protein and become functional structures. And then how many files do you need? It's about 20, 30 thousands. But more are genes that coding but not really become a protein. And then how big is the length? For a human, the size inside the nucleus, because we have 23 pairs of chromosome, so the length would be like 1.6 centimeter to 8.5 centimeter from this to this. But it's big enough that you can visualize. But it's condensed into a size of 5 micron in diameter in your nucleus. How amazing, right? And when you want to think, or when you listen to my lecture, you have to find all different files in this 3 giga. How can you do such an efficient thing? Even a computer would be difficult to do that, right? So this is the mystery of nature. After evolution, you got your molecular machine in your body. Okay, so to understand the life form, one of the major challenges would be how can you decode the sequence? This is an old story, but still very interesting. So after Watson Crick discovery of DNA as a double helix structure like this, and many biochemistry further decode the structure of DNA. And this DNA is consisted of the ribose and the base, and in between the base is the hydrogen bond. And between the ribose is a phosphodiester bond. So when you incorporate another base, there's a hydroxy group. And so if you incorporate with a ribose that has only a hydrogen here, it won't be able to polymerize further. And this is the secret for how to read the genome. So anybody here know how you encode the genome? If you know, you also got Nobel Prize again. So there's opportunity in the unmet needs. And so there's a clever guy. He used the chemistry so that he provide the dideoxynucleotide. For example, the dideoxy, dideoxy A, dideoxy G, dideoxy C, and dideoxy T, and to perform the polymerization. So when adding these intoxicate nucleotide into the normal nucleotide, you can see that sometimes when the cell do the polymerization, they just so bad in luck. The first incorporated would be T and become the dideoxy. So it terminates here. And maybe this guy is luckier enough. So the first one is the correct one. So he can polymerize the second one and stop here, etc. So then there will be a different length. And then they do electrophoresis. And then you can read the sequence like this. A, right? Then C, then A, then C, then G. AACAGC, right? Very simple, and that's how the Nobel Prize was honored to this guy. It's called Sanger's method. So this is how the gel looked like, and it's in 1970s. And that's when I was a sophomore student, a little bit little than you guys. And I was in the laboratory, and I have a pen to annotate all the sequence. And you know, this is so tedious job, right? So at that time, there's a guy in US called Steve Jobs. He invented the first PC. And this is how the Apple II looked like. You could see it in the museum. Yeah, but in Taiwan, we have a lot of so-called Apple II clones. So the same in my university. So computer, when they invented, always the number one user would be the gamer. So at the 70s, 40 years ago, not that different from you guys. So people always have the joystick and play games, right? But very few people crack open the computer and the joystick, but I did. So I know inside the joystick is actually the 2 variable resistor. It's a 120K ohm. So because there's a 2 joystick, so you can PK with your competitor, right? So there would be a ATCG, 4 different codon, 4 different codes that you can decode the job. So I reroute the circuit of the joystick. So we have the x-axis, y-axis, x-axis, y-axis, and I changed the variable resistor become a cadmium sulfate photoresistor, and then use the 5 volts to trigger the vibration, right? When you got hit by your competitor, the joystick will vibrate, right? And that's because the computer sent a 5 voltage signal to the motor inside the joystick. So this 5 volt signal would drive the LED. At that time, we only have red LED, unfortunately. So in such a way, when you have a motor to drive through this gel, you will read out a signature like this, and then you can do an automatic sequencing, so that you no longer need to, do the tedious work in the lab as a research student. So this is the draft I did about 20 years ago for how it worked. But this is finally become failure. You know why? Because the word is not perfect enough. You know, when you run a gel, sometimes it looks like this. So when you're rolling through your gel, it will be a disaster. And you will be kicked ass by your boss, right? Because the readout would be tedious. Would be, very outrageous of the code. So, at that time, I started to think, what can I do? And that's about 1 year later when there's a first image grabber introduced by Targa. We call Targa image grabber with a CCD camera. So you can take an image like this and then translate all these images become pixels. So I started to learn how to program instead of a hardware control, but become imaging processing. So I do the pixel to pixel 2D logistic algorithm development. And later on, because of the time, adding time, so they'll become a voxel, because then there will be a volume as a function of time. So then I switch from the pixel to voxel logistics. But finally, this doesn't really work quite well, because the gel would be very terrible. I mean, there's a lot of different issues. I won't speak in detail here, but then I switched to my CT-MRI application of the same technology and published my first paper in 1990s in IEEE, and another paper in 3D recursive tracing algorithms, etc. So this is a failure story about auto sequencing before decades before Illumina. Nowadays, you have a lot of auto sequencer available, from the fluorescent-based methods to the iron torrent, and these are all the semiconductor-based sensing. And you will be surprised that the next generation sequence chip, about 75% was made in Taiwan, although they label with Pacific Bio or Illumina, but they are fabricated by companies in Taiwan. And so what I want to say is, how about you guys? What's your solution? What is the unmet need of the sequencing? Currently, they are still take time to do the sequence. They are error prone. Do you know how serious that is? If you claim that I am 99.7% of accuracy in sequencing, you won't tell you and a chimpanzee, right? Because we share a lot of commodity, right? And between you and banana you eat during the lunchtime, it's 50% of homology. So that's a challenge, right? So yeah, so your opportunity are still there. I think yesterday people here say, asking, where's my future? One of your future is here if you dare to challenge. Okay. Another thing I want to inspire you is about the PCR. You know, all these sequencing algorithm was also based on another invention called polymerase chain reaction. Okay, everybody knows this is called Turtle Island outside of Yilan in Taiwan, but probably only few of you know that it is a volcano. And under the Turtle Island, there's a very hot area. We call it a hot spring under the sea. And if you think that high pressure and high temperature, there won't be any life form, then you are wrong. Because you can see that, oops, hold on. You can see that even the crab could survive. Meaning that if you eat your hot pot, right, with the crab, you are eating sashimi. They will bite you. Okay. But there's a clever guy called Carrie Mullis. He have insight about the opportunity. So actually, he started a company called the Celtus, and finally bought by the Roche. He found that if I could extract the DNA polymerase, meaning that this DNA polymerase could tolerate high pressure, high temperature, still polymerize your DNA, then you can simplify your DNA amplification. And that make a huge money. Do you know how much? Just a royalty from a single company is $2 billion. And not only you got rich, you got Nobel Prize, 1993, okay, in chemistry. Yes, so this is, this is polymerase chain reaction. I think there's a disaster about the movie. But anyway, so basically you just heating up, and then you denature the 2 strands of DNA, then you're cooling it down so the primer stick on, and then you're heating out again so the polymerase start to function, so the 1-strand DNA become a double helix, and then do it again and again and again. So this is the early stage DNA polymerase chain reaction. Use a robot to move between the 3 hot pots, 90 degree, maybe like 54, 72, and so it takes long time. And then later on, there's a semiconductor-based thermoelectric heater cooler introduced, so it becomes smaller, and using the heat block to do this. Then my student think, if you want to eat a lunch box in the 7-Eleven, how they do? Yes, microwave, and it takes like 15 seconds rather than if you use a cooker to cook your, maybe takes 15 minutes. So why not make this kind of heating or cooling mechanism at nanoscopic scale? So they make a nanoparticle response to photon. So now you can accelerate from the room temperature 20 to 100 degree by 8 seconds. So you just need to shining the light to control the PCR. And of course, they just like Elon Musk or Steve Jobs, they just start up a new company, and this is their machine. Yeah. So and because this is nanoparticle, so actually this could integrate with the chips, semiconductor chips, and they even do the so-called next generation sequence, etc. So opportunities on your hands. You just need to think outside of the box. Okay, so this is just a couple of different stories. I want to let you know my failure story and my student's successful story. Okay, the precision medicine, it is based on the fact that we are different. We are different. So with the same diagnosis, the same drug, some people got toxicity of the side effect of the drug and no beneficial effect. And some people, they got cured, they got benefit, and they don't have any toxicity of the drug. But before the whole genome sequencing or the PCR technology, we don't know. We just bet on the percentage of epidemiologist statistics. So what we want to do in the next century would be, now this century, sorry, would be, can we give the right treatment to the right patient for the right disease at the right time in the right person and even at the right dose. For example, you took ibuprofen and your enzyme, the metabolic function of your enzyme is so good, so it converts so fast. But your neighbor, your metabolic enzyme may be slower. So if you take the same medicine, actually your bioequivalent would be different. And now our regular medical treatment, we didn't consider that variation. So the idea would be, can we, from the genome sequence and other related information, to do prediction about what kind of disease you're prone to have? Or when you take this medicine, can I predict your bioavailability? Can I predict your response to the drug? And personalized and preventive as well as participatory. We call it 4P. If you look at the after 90s, actually there's a lot of scientific discovery very, very fast and actually become faster. So you are in a very, very interesting age that there's a lot of available tools on your hands. For example, 1992, the first automated DNA sequencing introduced. And then, then the first personalized medicine was introduced in 2001. The Human Genome Project completed 2003, and cloning to create stem cells 2011. And now it's a precision medicine because all these are ready there. If you look at the medicine now we take, one size actually does not fit all. For antidepressant drugs, only 38% will work. This is by statistic. But for certain genotype, it could be almost 100%. For other, would be 0%. Because if you're from your own, if you are a cancer patient, and I told you, I use Herceptin, you got 70% of cure rate. Then do you want to accept that? You would say, for me, I would either die or I cure, right? To me, it's 100%, but for statistics, yes. That's why we want to push forward for the precision medicine. And there's even others, like asthma drug, 40%. The worst is the anti-cancer drug, 75. Okay, so one size doesn't fit all. That's one of the reasons we want to push through the personal medicine. For cancer therapy, if you look at the history of development, from a small molecule to antibody drugs or macromolecule drug to cell therapy, actually the whole world is marching through more and more of the precise in therapy. For example, like a carboplatin, 5-FU, they are DNA chelating agents. So basically, they go to normal cell as well as to cancer cell. So you got intoxicated by the normal cell and also by the cancer cell. But when it's moved to the adaptive immunotherapy, like a CAR T, they start to have higher specificity, although not 100%. And then if you looking at all those EGFR mutation-based targeting drugs, they are so precise, so that we can know if you have a sequence telling you this is this kind of mutation, I can tell you, well, you could be treated by this third generation drug, etc. And this is another example about what my laboratory did. We have been working on new drug development, and from the screening we found that they are very toxic to an array of head and neck cancer, but not toxic to fibroblasts, keratinocytes, endothelial cells, etc., kidney cells. Yeah, and this is true not only in head and neck but also in colorectal. Okay, you would be very excited about that, right? But don't be excited too early. So next thing, what you do is you look into the same head and neck cancer pool, maybe like 20, 40, or 100 cancer cells, and you would find that there's always resistance and sensitive cells. And of course, for precision medicine, what you do is you develop certain way to screen out that these guys could be treatable. So you say, I can give you this medicine. And these guys say, oh, sorry, I cannot cure you, and you should visit another doctor seeking for help. So that's the current precision health. And what we do is, from these sensitive cells, we could, through a process, to let them become more and more resistant by intoxicate them with higher and higher dose of the treatment. And finally, you got the resistant cells and the sensitive cell, but they harbor the same genome type. And when you have an array of such kind of cell, then you can do a genome-wide sequencing, like exome sequencing, etc. Then you find what's the difference between the wild type and the resistance. And then you started to know, first, you could distinguish which patient could be treatable, which won't. And then you treat those that is treatable. But if you are more aggressive, you would do this. You're trying to map out what is the signal cascade of the resistance phenotype and what is the center of the mechanism. Then you can develop adjunct therapy and then make sure they don't harm the normal cell, which is market rate. So in such a way, you can treat the untreated, this is resistant cell, and then you become more sensitive by combination. Still not compromise their body weight and not giving toxic side effect to the body. So this is just an example for what we develop drug nowadays as compared with old days that we always just screening for the cancer cells. Yeah. So actually cancer treatment will be the first to introduce the precision medicine in the therapeutics. Okay, and so so that now it will be kind of individual cancer based on the specific genetic abnormalities that one patient could harbor. But unfortunately, many cancer cells, they're prone to mutation. So you like tracing a guy that changed their cosmetic all the time, right? So there should be a more better strategy to deal with this. So there's a paradigm shift during the treatment, clinical treatment. From the old days, the patient population base, as I said, I tell you, you got a 17% of cure. And you said, for me, it's either 100% or 0%, right? Then to this kind of stratified treatment, which was first introduced, for example, the breast cancer. When you got a breast cancer, you do a biopsy, and then we're standing for your HER2, and we're standing for your hormone receptor, etc. Then we give you the treatment. And then the lung cancer, which is even more precise to the mutation type. So the disease subtype, the risk profile, the demographic, socioeconomic, clinical feature, biomarkers, and molecular subpopulation, more and more precise. Then would it be to the personalized medicine, even considering giving you the the third generation anti-EGFR TKI drugs, then I consider metabolic to that particular drug. For example, I will sequence your cytochrome, which is responsible for the drug metabolism in your liver, and decide what kind of dose I should give you, rather than give you the so-called standard dose. And so that will involve the genomics and omics, the lifestyle, the preferences, the health history, etc. Yeah, so we are marching from this side toward this side, and there's a lot of others involved. For example, the medical imaging, the microbiome, as our previous speaker just mentioned, the omics, and etc. So why we need precision medicine? It was patient treatment centered, with omics and diagnostic data, with exogenous other data, and the clinical and the real-time monitoring, that we could support a better management of the patient's disease. And this will give an increase in survival rate, provide effective and safe treatment. As I mentioned in previous example, that we could kind of tell you when, although if I just use a general statistic, I can tell you there's a 70% of cure rate. But when I do HER2 staining and you are positive, then I can tell you you got 50%. And then if I find that the HER2 staining and then I do the whole genome sequencing and you fit for this treatment, maybe you could be treated at the 75%, etc. So when you get more and more information, the cure rate would be better and the side effect would be reduced. In the target disease with greater accuracy, as I mentioned, and migrate a necessary treatment, mitigate a necessary. So if you are HER2 negative, why bother using Herceptin, right? Yeah, Herceptin. And reduce prescription error and reduce healthcare costs and reduce over adverse drug events, etc. Yeah, so there's a global trend for precision medicine. We can see that in USA there's such big funding in the precision medicine field, and also in China, UK, and Japan is as well as Taiwan. And this is the funding period, and the field mostly focused on the cancer. And establishment of biobank is a fundamental part for the precision medicine. So many countries already devoted significant efforts in those. Yeah, and if you look at the ecosystem as in the precision medicine or precision health, there are different domains that you guys could contribute as your future career. For example, in the service side, there's a health prediction model, there's a drug development and diagnostics, clinical evaluation, treatment, post-operative evaluation. And for the technique side, DNA sequencing, proteome, liquid biopsy, bioinformatics, drugs, radiation therapy, surgery, mobile device. And they co-contribute the testing services, diagnostic services, the treatment mostly in a healthcare provider, and the monitoring services, such as Guangda yesterday, and the healthcare, health life consultation, which is to be developed. So precision medicine from 2016, it's only about $42 billion, is expected to grow tremendously to 2025 to the 149 billion US dollar in the market. And within the market, the detection and target treatment would be the largest proportion of that, followed by remote care and clinical data. And the global pharmaceutical drug market also will have a tremendous growth. We can see that although there's a growth, overall growth from like 1132 billion to 1331 billion, the most rapidly growing part is the precision drug, such as the mutation-based therapeutics. And another significant part is a companion diagnosis, which means that when I introduce a drug, I also introduce a panel of biomarkers that predict the efficacy. So when you have a clinical visit, I do a clinical test first, and then I select which kind of drug would be best for you. So there would be core resources in R&D and talent pools, as well as funds that government should do, and then external environment, the policy makings, the regulation side, and the market. So the ideal model would be the users, and they could provide the data, and all these data to the data analytic tools to generate a model, and then this decision support then to the patient with a better health outcome, and then feedback again. This is how we expect the genomic-enabled learning health system. Taiwan government has launched the 5+2 industry, within which actually one of the emphasis is in biomedical industry, trying to upgrade our industry infrastructure and ecosystem. As I mentioned yesterday, we want to move toward from the more lower-end medical devices to class 2, class 3, more higher-end, more technology and knowledge-driven devices. And then build the biomedical clusters, connect to the world, and pursue the industry of the future. So this is how we do from the Nangang to Kaohsiung and Pingtung. We build up science clusters based on our existing science parks and the new science park. For example, the Nangang Science Park. There are 468 companies there. And in Hsinchu, since we have ICT, so we try to bridge between the ICT and medical device and medical imaging services, as well as some are new drug and biologics. And in central Taiwan, we try to build up the precision instrumentation and rehabilitation industry. And in southern Taiwan, the focus is in implantable device and biomaterials. And Pingtung mostly in the agriculture side. So this is to bridge from the precision medical programs in Taiwan, trying to bridge from the fundamental science to the hospital. So we fund the Academia Sinica for the focus on the so-called biobank, the genome sequence of healthy population and specific disease, and also the NHRI. And then we established the database. NHRI mainly focus on cancer and metabolic diseases, and then NCHC to build the infrastructure, which is the National Computation Center. And we also have the, since this is finally want to lead to the product development, so we have the product development part, focus on the development of CAR-T related concepts and companion diagnostics, as well as others. And we established the Taiwan Clinical Trial Consortium, as I mentioned yesterday, so that we group the outstanding clinical trial centers as one in Taiwan, and then the hospital as the final test bed of the products. Okay, so for the Taiwan Biobank, we have the two parts. One is a community-based, trying to know what is the whole genome profile of the Taiwan population, and the hospital-based, mainly focus on disease-specific genome sequencing. Yeah. So between the MOS and NHRI, we're trying to, and the NCHC, trying to foster this precision medicine program. And there's a funding about 200 million per year in this part. So these are just some of the highlights about, for example, the gene mutation viewer is a startup company that work on this precision health program, and including introducing the database together with AI and toward the commercialization. Okay, so these are just a glance of the how we team up from the Taiwan Biobank database, the NHRI database, and National Health Insurance. Taiwan has digitalized the claim data since 1996. It's one of the earliest in the world. And we are centralized insurance, so the coverage 99.7% with a significant population, about 23 million populations. And we established Taiwan Clinical Trial Consortium and a laboratory, development tests, as well as strong government support. And then there are university-based, and there are Academia Sinica, E3, and NHI, as well as DCB, to serve as an intermediary for the translation of these fundamental resources toward a healthy growth of different companies, from the database company to the reagent development and biochips to software services and the antibody production platforms, as well as new therapeutics and CRO, CDMO, etc. So in the diagnostic part, this is Taiwanese companies, the profile about their growth, and within which many companies start to focus on biomarkers and sequencing services, as well as companion diagnostics. And the pharmaceutical, this we just mentioned about this. And precision medicine actually could be local, regional. For example, this is from Professor Yang study. We found that in Taiwan population, as well as the Chinese population, the EGFR mutation is much higher than the Western countries. So that what has been done in the Western country doesn't mean it will fit your patient in Asia Pacific area. And that gives you opportunity to further develop in Taiwan. And this is kinase inhibitor. You can see that there are kinase inhibitor is actually the second most sought after drug targets. And you can see from the 2001 till now, there's a more and more different kind of drug introduced to target different kind of mutations. And for example, head and neck cancer, there are more than 90% of EGFR mutations yet to be treated. Okay. So new drug development, for example, DBPR112 is a new drug from the NHRI targeting at the exon 20 mutation that has no competitors yet. So I think this holds a great opportunity for the precision medicine. And another strong part is Taiwan's clinical trial. From the 2015 to 2018, we have a rapid growth of the clinical trial approved in Taiwan FDA as well as US FDA, meaning that this is a growing opportunity. And there are more and more companies introduce new drugs to the clinical settings. And within which you can see that they are growing part of the precision drug in the fraction. Okay, so just give you an example from 2014 to 19. These are the drugs already on market, meaning that these companies already generate revenue from selling these products. For example, the Besremi is treating the side effects of the cancer treatment. And together we also have more and more of the devices, including the companion diagnostics, and most of them more and more are in the high-end device, meaning that class 2 or class 3. So Taiwan is growing in kind of marching, not only aiming for the growth in total revenue of the medical device and pharmaceutical, but we try to shift the paradigm from the general purpose toward more of the high-end medical device and the new drugs rather than Me Too drugs. So the government has done a lot, although it's not always not enough. We changed the regulatory part to encourage innovations from the academia. And so we actually released the professors to become a CTO or even CEO in the new company, especially in biotech. And then we have the amendment to Industrial Innovation Act to give incentive for new startup and de-risk those people that have the courage to start up new co. And we have a different strategies to accelerate global sale of innovation drugs and development of precision health care just end of last year. And also the amendment to the Fundamental Science and Technology Act to kind of encourage commercialization of scientific innovation from university. So the way that most do is we kind of fund universities. It's a competition based. We call it Gloria program, the global Gloria, globalization, whatever, which means that we give a funding to the university, and the university has to find their industrial partners, forming a club. And these partners are not free. They pay the university annual membership, and so that they could have the opportunity to see the most front-end innovations in the university and bridging them toward the industry side. So this is one of the programs we have been done and very success. And within that Gloria program, the university can hire professional CEOs and COOs, pay their equivalent salary to the industrial level, so that the translation could be adequately promoted. Yeah. And then we select like cell therapy and regenerative medicine as well as precision medicine as the focus of our nation to develop in the biomedicine. So that last year actually we become the second country to pass through the cell therapy regulations. And we will struggle very hard to the Congress House to pass through the regulatory page about the reagents of the cell therapy domain. Yeah, so, and this is an event we just celebrated recently, and we host the BioAsia in Taiwan for the first time. And there's more than 1,500 conference attendees, which is tremendous, and more than 25 countries participate from the globe. So now we are able to attract people to Taiwan because we are so innovative. And there are 1,600 exhibition booths, including Taiwan and the foreign countries, and more than 2,000 one-on-one partnering, so that when you have a new startup, you won't be lonely. You have opportunity to engage the investors, not only domestic but also international. And if you have product to sell, you have opportunity to seeking for channels to sell your product internationally. Yeah, so that's my talk. Thank you.
So, any question? Professor shared here not only cover interesting research, his own research, but also the prospect for this, you finding a good job in this precision medicine. Looks very promising. It's has just started. Yesterday, I remember some student asked me, which startup company he want to form, which area he should choose. Of course, there are many important criteria, but one of this is, of course, you want to choose a field that is about to begin to become important. And that's the earlier you get in, the better the probability you succeed. So this is certainly one of the areas, looks like many possibilities. Yeah, I was impressed by one of your slides that has itemized which area, etc. So this is pretty interesting. So maybe you have a question? Yes.
就只是一个小问题，就是刚刚有一张图是在讲台湾和美国 FDA 的 clinical trial， 可是美国的比台湾的还少，这是正常吗
？OK， 这个跟这个很正常，这个跟那个 marketing strategy 有关，就是说一般我们会做临床试验的话，跟你的那个就是未来你想要卖的国家还有跟法规有关，所以如果你今天然后这个也跟这个疾病在什么地方流行有关。 举例来说，肺结核，你可能不会那么想去美国那么先进的地方，对不对？除非是那种 multi-drug resistance 那一类的啦，哈。但是相对的，如果你是讲 lung cancer 啊 breast cancer， 那你首选当然是美国。所以这是纯粹是商业性的考量啦。你在哪里做这个 trial？ 那现在很多，其实这个应该问那个杨校长，他做好多 trial， 对，怎么去选择你的 first landing place 在哪里，然后 first in human， 好，然后当然也跟 cost 有关。我不是这方面专家，我就是就我所知的回答。
因为有看到说，好像台湾现在有开放细胞疗法，
对，
那台湾有真正有做所谓的细胞疗法的 case 吗？
因为才刚开放，所以现在很多是在 review process，在卫福部的一个审查的，我印象中应该是有第一个已经是 pass 在开始收案，
所以已经有提出申请，
对
然后也有核准这样子。
对，但是就是still is a review based process。那现在还是以就是自体的为主啦，哈。但是将来就是我想将来要 industrialize， 其实还有其他的考量，慢慢其他的法规需要通过，
因为好像看到日本的教授，他们已经讲到，他们日本已经有试着用自体干细胞，然后开始做治疗这样的一个 case 了，这样哈。
是台日其实合作很密切
教授你好，我想问一下的就是，在目前来说的话，大部分的医疗的行为必须要根据治疗的指南来做。那么在以前分层就是 stratified model 的时候，就这个共识比较容易达成，就是针对一类的疾病，癌症也好，我们可以给他把病人分成几个类别，然后来形成一个专家共识，然后医生在治疗的时候就根据这个指南来具体的一步步做。那么在精准医疗的时代呢，越来越多的基因也好，各种的个体化的这种个人的体征的特质被囊括到了这个治疗的考量当中来之后，那么会不会就是形成一个非常复杂的分支非常多的一个指南的一个形成？那么专家之间的共识是不是就会更难达到？那么作为医生来说，如果你面对的一个患者，他是非常小的那一部分人，他有可能他有自己的一个非常特别的体征或者突变。那么我们知道医疗必须是 evidence based， 那现在是循证医学。那么作为一个临床医生，有可能没有办法组织有效的临床实验。那个时候你怎么决定给他的用药的种类或者剂量？就是不是以后就会造成这样的一种混乱？
应该不是哈，就是说，其实整个医疗的体系呢，如果你去看100年来，其实已经改变很多了。那其实事实上，现在的一些诊断的 guideline 也已经从以往就是说你刚刚讲的这种 stratified based 的，慢慢走向 precision。像昨天这个杨校长有提到，假如你 got 这个 mutation，then you are eligible for this treatment。现在已经到这样的程度。那未来可能会用系统性的东西做。那到了一定的复杂度的时候，其实你也不用太担心，因为现在 AI 越来越发达了哈。然后那个 decision making 变成一个 logistic 以后，其实，台湾的 MD 应该都聪明 good enough 去 make 这个去 make 这个 judgment， 所以我想应该只会对病人越来越好，因为我觉得治疗这件事情，就像昨天有同学讲的，不应该也包括杨校长提到，不应该就单纯是产业，它必须是以人为本就易位思考，假如你今天是病人，就是我是病人，你是医生的时候，我会怎样的角度去思考？那这个 guideline 的话 ，always 是 evidence based 的。那其实 FDA 现在已经慢慢也在改了。其实 FDA 有些药物它的 approval 已经是 based on what kind of mutation as indication rather than what kind of cancer。OK， 所以这个全世界整个趋势都在改，你不能墨守30年的 rule 来看现在的这个世界，这样。
我帮你补充一下，其实current practice in medicine here, actually you have to follow the guideline for every clinician. Actually, in every field, you know the guideline. It is updated every year. Even in lung cancer, the guideline may be updated 3 or 4 times within a year. So every clinician need to update the current status of the guideline for the treatment for every individual disease. And because of the National Health Insurance and the big data and the electronic medical record, even in the clinical practice, if you prescribe a drug and in the medical information that the patient had a history of the allergy to that kind of drugs, in your computer pop out immediately. Don't prescribe the drug.
Yeah.
Yes. So we try to keep safe for every patient you see. Yeah. But I do have a comment for 我们次长，你可以秀那一张那个 precision medicine。我们在 develop precision medicine 的时候啊，其实我都一直觉得我们国家很有钱。也很没有钱了哈，但是就在很少的 resources。I will explain in English later 我其实是比较期待的是在最少的资源能够做最多的事情，但是我们常常就是浪费很多资源，但是没有办法得到最好的效果。那在这里就是你会。这么多年来，10几年来，我们在做 precision medicine， 但是 come out 有什么东西真的拿得出来，或真的秀出来说我 patient benefit 有一些 precision medicine， 那其实好 precision medicine 或 precision health， 你 target 在哪里 ？patient， 那你病人在哪里 ？hospital， 那谁在 practice precision medicine？ doctor。假如你所有的医师，你没有好好 educate 他有 precision medicine，come on nothing， 做的东西没有人用，病人不会 benefit， 所以你必须要你的医师 educate， 然后有一个大家有这个 concept， 大家希望往这个方向走，然后他必须要 disease specific， 你没有 disease specific 乱枪打鸟，永远 come out 不会解决问题，应该是一个病解决。在这里最大的问题是医院没有 engage 进来。我其实要讲的事情是，原来科技部一直在帮忙做那个，跟卫福部一直，台湾好不容易 set up 台湾 Clinical Trial Consortium。有13个病，然后现在卫福部希望把 cell therapy 放进来14个consortium 是把所有的 medical center， 台湾最 common 的病，每一个 medical center 大家把 electronic medical harmonize， 那所有的 clinical trial harmonize， 那所有的 doctor 所有的 patient recruit 进来，那所有的 doctor 有共识要把他这个病治好。precision medicine 应该把从这14个病。14个 disease category， 14个 consortium， 每一个 consortium 好好 pick up 1 or 2 disease， 好好 implement precision medicine， 很容易从健保的资料，从 prospect 的 clinical trial， 很容易 come out 很重要的事情。但是我是建议你 revise 这个东西，把那个部分放进来，因为这样才能够真正 implement precision medicine， 你放到国务院 OK， 没有问题，没有医院不 implement nothing come out， 所以你必须要从那个他的自己 bottoms up 的 disease group 自己要一起 integrate 进来，才可能有机会。这个也是为什么我们跟日本 ARO， 其实我们的那个 organization 跟 ARO 非常像，那。只有这样才能够一个一个把它做好。I suggest that put the hospital and clinical trial consortium in this map of precision medicine. Ask the each consortium focus 1 or 2 disease in depth. Do clinical trials. Harmonize with Japan or international clinical trial consortium, and try to solve every disease. Implement precision medicine, then you can come out with good result. This is more efficient way to practice or to implement precision medicine.
好，这个其实是非常重要的建议。我们将来一定会这个，因为到最后呢，终端就是在 hospital 的使用。
I just would like to add, what Dr. Yang said in general is correct. It's the end result are doctors and
patient
or the patient. The patient is more difficult because you can ask doctor to do something, but the patient don't understand it, right? So the education comes from doctors and the hospital. Well, he said, well, you can assign one organization like NHRI, or it's useless. In Taiwan, there's only 2 ways to do it. One is national health insurance payment. Right? National health. If you say that if you follow the precision medicine guideline, the hospital payment will be raised. That's how to control hospital. Yeah, well, in principle. Of course, there are ways you can, many hospitals can use, right? And for the doctors, it's the same. If the national health insurance payment is raised if you follow the precision health guideline, the payment will be higher. Of course, you laughed. I know you laughed because hospitals are clever and the doctors even more clever. There's a way to bypass. We know that, but that's the only way in Taiwan we can do it.
Yes or no？ 其实是这样，就是台湾的健保其实做得很好。那举肺癌为例了，他其实吴院长讲的是非常对的，非常对的，就是健保假如非常严格的，你没有 follow guideline 的话，他就不给付这些药，所有的医师的 practice style 就 follow precision medicine。举一个例子，刚刚次长讲的，假如你有没有测EGFR mutation， 你就不可能用标靶的药，标靶的药非常 expensive， 但是 National Health Insurance 是 cover 它的，但是你没有 follow guideline，no， 我不给付你。那所有的 practice 就是 follow 这个 guideline， 但是有一些问题是这样，就是 guideline 不是完全正确。昨天有同桌的同学知道我讲什么意思了哈，就是老师讲的不一定是对，教科书写的都不一定是对的，校长讲的都不一定是对的。你 always 要存疑 ，always 要存疑。那 guidelines for Caucasian for worldwide sometimes 有一些是不一定 applicable 到 certain subset 或 population。所以你有一些事情是还是得这个 society 这个 consortium come out with a study to show that, then convince our national health insurance say, oh, probably here you have to practice like this way, benefit your population. 这个是这样，就是一定是要这样。然后还有一个是健保的资料，其实是一个很重要一个 resources。我们2300万已经施行20几年的健保，你看看那个 big data 非常非常重要，里面很多 garbage 没有错，但是里面很多保障。那其实卫福部跟科技部应该做的事情是怎么样把这个保障 dig up 出来。我举一个最简单的例子，讲 B 型肝炎就好了。假如 B 型肝炎肝癌里面的诊断绝对没有错。你哪一个人有肝功能异常，哪一个人有 B 型肝炎，多久以后得到肝癌，哪时候用 vaccine， 所有的资料跟死亡档串起来，有非常好的一个 big data。 绝对错不了。肺癌也是，肺癌什么样子的病人，他病理有诊断肺癌，绝对错不了，里面没有 garbage， 绝对没有 garbage。结核病也是一样，你 TB culture positive 的病人，他的影像是怎样，他的 progression 是怎样，用药结果是怎样，绝对没有 garbage。然后你把所有的这些没有 garbage 的东西憋到另外一个 big data， 全世界的人都会很想看，全世界 pharmaceutical company 很想看这个结果，来 design 他要做的事情。我是说我们是坐拥金山，而不知道好好去用金山的一个很难过的事情。还有一个 image， 你2300万20年，肺癌一年有13000-4000千个，这些都是跟健保拿钱去做的影像。delink 以后，你看多少 information？ 你要 develop 什么 AI？piece of cake。只是你坐拥金山，不会好好用金山了。这个，其实我还为了这个事情去跟政委好好讲说，我们应该好好用我们自己的 resources。
我想昨天那位同学应该听到了，你金山就在你面前啊，想办法赶快去做。刚才讲，其实我也在 surprise， 台湾没有 team 专门做这个事，其实是 data， 大家现在晓得，谁拥有 data 谁就是 king。
对
，whoever controls the data control everything。Yes. Everything depends on data. So if you have data, you don't need anything else.
Last year,
we have. Sorry. I just mentioned that national health insurance data I created many years ago. Okay. So it's going on well. But pretty soon, people found that there's treasure in it. So some hospital get together. They got this to the Ministry of Health Statistical Department. Now it's a mess because they are interested in it. Simple. So what you said, 我们坐拥金山，可是是我们的责任是把它弄好。所以记得我跟你讲过，你说好，以后我会改正。
不过我们去年开始把那个影像的 DICOM data 要求要 upload 的，所以未来就没有still 亡羊补牢。所以我们去年就是有这个法规啦。另外一个就是说，刚刚回应刚刚同学的问题，其实是规则是可以改的。像lung cancer 好了 ，lung cancer 的 therapy 以前那个就是 EGFR-TKI 是不是在第一线？可是我们经过了许多临床医师的努力，我们算是第一个国家把它 push to the first line， 救了很多的病人。对，所以我想这个是一个很重要的 remark。
我想昨天我听到那个石教授讲，美国通过那法律。就是你的 electronic data 从一个 hospital 一定要有给另外一个 hospital 也可以用。
这个很重要。
I think that's a great law. That's very smart. I think then the hospital solve their own problem. The software company will help you to solve the problem. Yes, then it will be very easy. Otherwise, you have to find a special team to do that. Very complicated. That's a great way of solving problems. Actually, software is not that difficult. It's just they don't have incentive to do it. If you have this law, then they will do it. Do it much effectively. So I think we need a law like.
谢谢。就是我想问几个问题。首先，第一个就是刚才我看到有说精准医疗也要用一些监测仪器，包括 mobile device。就是在这一块的话，有什么样的合作和投入？然后还有一块就是现在其实就是有没有想过去把这个人才培养的这个制度给它更新一下？就是因为医学生的话，有没有想过要去让他学一些和数据有关的东西，和 AI 有关的东西，这样可以更新它的一个知识库，这样可以培养更前沿的一些人才。就这2个问题，谢谢。
The second question would be the talent cultivation. I think diversity is great. So, as a medical student, if you are in a comprehensive university, actually in Taiwan, you can take any course. You can go to EE, you can go to informatics, you can go to material science. We want diversity. And we want you to make friends so that you don't need to do coding by yourself, but actually you can do coding by your neighbor. And you give them idea and you can do collaboration. I think the world is becoming more and more of network-based, teamwork-based, synergy. So I think that's important. So actually I encourage medical students to think outside the box and take courses that they normally probably not taking. Even the economy course would be very interesting. Trying to solve the health insurance issue, right? So we need actually very diverse pool of talents. So yeah, that's the second question. And actually most do have program to cultivate students, especially graduate students. We not only have the RISE program to send them to industry for collaboration when they are doing project or thesis in campus, but also we send them abroad to, like, for example, Stanford, Berkeley, MIT, and also companies like Roche or like Merck, Sanofi, etc. So we do have programs, and it's competition-based, of course, because we have limited resources. So that's for the second question. And for the first question, can you just elaborate more?
就是不是说精准医疗里面还是要使用到一些监测仪器，比如说。
Okay. Got it. So mobile device, I think there are a couple of issues. Actually, both industrial side and academia side is on the way to solve. One is the data security. For example, if you want to do the wireless transfer of your data, there's a regulation. For example, there's a Bluetooth, we call it BLE 4.0, which has a so-called medical compliance regulation. So if you want to use the Bluetooth to transmit your data, especially medical data, when you do the coding, you have to comply with that regulation. And you have to read the description. I think the EE people would know. So this is for the BLE compliance. But in the future, we may have 5G. We may even have 6G. And the medical compliance haven't coming out. And that's why we urge to participate in so-called International Standardization Organization, the so-called ISO. Because only if you are insider, then you know how the rule was made, and then the industry could follow and could prepare. Yeah, because, medical things is highly regulated. Yeah, that's why Apple Watch is not a medical device in Taiwan, but in US, yes.
教授好，那个咱们这次科学营主题就是精准医疗，然后您刚才也一直在提，就是我们用药也应该越来越精准。但是与此同时带来一个问题，就是药厂研发一个药的话，它所花费的越来越高，但它的受众是越来越少的。与此带来的问题就是药越来越贵，看病也越来越贵。以您刚才提到的一个药物 TKI 药物为例，就是说，里面用的最好的就是伊马替尼，然后治疗 CML。就是我不知道在台湾是怎么样的，在大陆大概一盒要2-3万人民币一盒，1个月，然后它需要一盒，就药费是很高的，对于一般家庭是很难承受的。对。然后所以说怎么说呢？就是我可以理解诺华研究这个药物，它花费了很多钱，然后但是虽然它面向全球，但是只针对于 CML 这一个单一群体，然后人是很少的。我可以理解它在短时间内专利期内要收回它的投资成本。就是我想问您一下，就是 您如何看待就是这个药价可能未来会越来越贵，然后以及是如果您觉得这个问题存在的话，您如何看待整个问题？
好，我想几个面向来看啊。第一个就是说，刚刚提的那个药，其实台湾健保有给付。OK， 不用钱。为什么有给付？我跟你讲，其实就是为什么我说医学生呢有机会要去修经济学。因为从经济学的角度，虽然你看到单一药价很贵，可是它其实是 beneficial 的 for the health insurance， 而且我们已经算好在多少钱以下我们还有赚头，所以必须要去跟药厂杀价。那很简单嘛，因为我99.7%的 coverage， 所以我可以跟你讲说你全有或全无啊，你全有或全拿，因为现在很多药。很多 mutation 的 drug 不是只有一家，它有 competitor， 所以3家我们就很好玩啦，就说，OK， 所以 you know this is purely economics question. Second 就是说，面对那个药物越来越昂贵 ，is that true？ 不一定 true。其实以前有很多的药物，其实你只是没发现它其他的功效。那因为现在的 bioinformatics 越来越强，然后现在工具越来越多，所以很多老药被 reposition。OK， 那 reposition 以后，那边有专利了，所以相对上它的 cost 就比较低。OK， 但是它是 more effective。还有第二个，现在更多的 combination 出来，最有名就是艾滋病嘛，对不对？那所以很多药物变成 combination 的时候呢，那其实这些可能都是已经专利 expired 的药。OK， 那另外有一些是剂型的问题，比如说我们知道有一些药，它吃了半天，到达你血中的浓度超低的，所以病人都要去门诊打针。那你知道门诊一个 nurse 在那边就是一个 cost。如果今天你有一个新的剂型，用鼻子一吸就进到你全身循环，那医院就省了那个 nurse 的 cost 嘛。这个 nurse 可以做其他事啦，我是说，但是我的意思是说，这个其实是一个 formulation 的改良，所以其实 there's a lot of opportunities。我们就是要从那个盒子外面去想 ，think outside box。各位有很多很多的好机会，相信我。
Thank you very much. Very exciting, provocative presentation. I really appreciate your I appreciate very much your Taiwan's approach of precision medicine. But we are now aging, we are living in quickly aging society. So the social burden is surge, exponentially growing, and accompanying with aging populations.
Yes.
So our government, Japanese government, are now very, very struggling how to cost contain the caregiving for disabled peoples.
Yes.
And also how to cost contain. The precision medicine is okay, but now the cancer drugs, I'm a chemotherapist, old-fashioned chemotherapist, but now that the cost for cancer patients the doubled and the tripled.
Yes.
So we need to be more bright to cost contain and the balance. And the most important point for maintain the sustainability of the nation's activity and the happiness, the most important point is prolong the healthy lifespan.
Yes.
Healthy
aging.
Expectancy.
Yes.
Yo, is there any, we need anyhow deep thinking.
Yes.
And AI can help or solve this problem or not. And precision medicine how can support this or solve this problem?
Yes.
Is there any ideas?
Yes, I think both Japan and Taiwan is trying to develop, we call it healthcare robotics. The robotics not necessarily look like a human, I would say, but rather it's a kind of using the sensing and AI circuits and respondents to help aging people and to kind of make them able to contribute to the society so that they can live happily and have the kind of satisfactory in mind. So I think that's important. So that's why we got opportunity, because both Japan and Taiwan, we are very strong in ICT and software, as well as automation, precision, instrumentation. And from this industry and cross the border toward healthcare, actually both sides, government put a lot of efforts, so does in Taiwan. So I think that's one thing that we're trying to use the AI and IoT to help the aging people to enjoy their life, and they can still contribute. Actually, in Japan, there's many aged people. They still contribute to the society. They do good work. They still have very good body status, and so does Taiwan actually. So I think that's one thing. We promote health rather than treat disease. And the second issue would be how we effectively treat disease. And the answer is treat disease at their earliest stage. Just like Dr. Yang mentioned yesterday, it is better to prevent than to treat. It is better to treat early than to treat late. And the cost is like this. If you treat in late, it's like this. If you treat early, like this. So that's why we need a better system and a faster system. For example, as I mentioned, like the invention my student, they startup. If you do a quantitative PCR, if it takes a day or a couple or a week, then it won't be useful for clinical setting, because the outbreak already began, and all the village-aged people will die and will be severely hospitalized. But if you think about it, if this diagnosis would be 5 minutes, that actually game change, because you can quarantine immediately, and that's it. And then the rest of the aged people could live happily. Yeah. So I think technology will eventually help this issue, and we are in a running race with time, because Taiwan is marching from the aging society to extreme age society, and so does Japan. So we have to, collaborate.
We should stop here. So let's thank the Professor Xie.
Thank you.